Hi, thanks everyone for, thanks to the organizers, and thanks for everyone coming to my talk to listen to me. This is mostly an experience report. There's going to be a little bit of technical stuff in there, and there's going to be a bunch of opinions, somewhat like the talks we had this morning. So there are three themes running through this talk. Distributed programming. I'm using that in term for the large idea of distributed programming, including concurrency and deterministic and non-deterministic parallelism and so on. That's a big subject. Just going to touch on that. Cloud Haskell, which is essentially a library and a set of libraries. I'm going to describe that, and then finally I'm going to show how we use those ingredients to do some actual work, and I'll briefly outline the status of that. But before I do any of that, I'll just explain a little bit of who we are. So Dragonfly Data Science is a small firm. Those are a few of, that's pretty much half of the organization. And we're based in Wellington, and I don't know if anybody's heard the term data science before, but it's often described as being the intersection between mathematics, statistics, modeling, programming, developer community, and actual science, papers, research, and so on. And essentially, that's exactly who we are. So the team consists of people who have science background. We write papers about sea lions and language recognition, and we have guys who are experienced with databases and writing code, and I've been involved from the get-go. I'm probably there's two of us who sort of founded it, and I was really interested in the talk we had just before lunch, where Alistair was talking about foisting choices, technology choices on your business partners, and I did that, and it's definitely a risky move, and maybe something that you have to think twice about. And when I started with Ed, that's Ed on the left there, he was really, no, we're not going to use Haskell. What are you talking about? That's insane. And after a few years, I beat him down, and now I feel like we're making pretty useful progress using Haskell. So, okay. This talk is really an example, one sort of experience report, essentially, of the kind of things we're doing. Okay, so distributed programming is everywhere. I might just turn this thing on, sorry. Oh, excuse me. Forget. So I guess there's a few things here. We all run into these problems. When I started as a developer, God knows, some time ago, these problems were newish. Client-server architectures were newish. Multi-core things were being talked about as a possibility, and high-availability orchestration was something that you might have to do. Now it's kind of the norm. Now it's everywhere. Everybody's dealing with these problems all the time. This is the context that we work in, and we need to be able to think about this differently. We need to be able to think about this using the right concepts. My dad was a Fortran programmer, and he talked really excitedly about discovering the pattern of subroutines. So the Fortran community, when they first started, were using goto, and there was no such thing as a subroutine. It's a pattern that emerged. I think we're in that phase in this context. We're all moving away from reasoning about programs as single-threaded concepts to having to confront all of the issues that appear. So in this particular distributed programming context, I'm really interested in threads that are running on different machines and coordinating their activities across Amazon and cloud infrastructure. That's kind of an essential capability. and it's all about that communication in the end. Asynchronous communication is what you have to think about. So there are these kinds of issues that come up repeatedly. That how do you stop deadlocks from happening? How do you ensure that your state is consistent all the time, everywhere? And tolerance to those faults that inevitably occur because you're actually sitting across infrastructure that's potentially in different time zones. And managing this asynchrony is, if you look around all the languages that we're talking about here, but in even more broadly across Swift and the latest C++ compilers and so on, they're all embedding into them primitives that deal with asynchrony. JavaScript, everybody has got it, and they're all thinking about it in ways that are slowly kind of coalescing around some certain key ideas. This book is, I want to point out, is probably one of the best books on the subject, in my opinion. And one of the key aspects of this is that he talks about it from the point of view that there's a whole lot of different problems here. There's a whole range of technology choices and patterns. There isn't a single solution that solves every problem. What you need to do is understand the breadth and range of the problems and the solutions. And of course, Simon is an outstandingly intelligent, capable man who understands these problems very well. It's really well written. And this is how I started. Simon wrote a library called Async, which is the standard Haskell library for dealing with concurrency on a single machine. And the Cloud Haskell people borrowed a lot of the ideas out of that, and a lot of the primitives are there. So yeah, I recommend this. So the other inspiration for this is Erlang's OTP libraries. So Erlang has the pedigree to be able to say that it's running masses of infrastructure all over the place, and it's working, and it's battle hardened. And this Open Telecom platform, which is, by the way, the most terrible name for a library, I think. It just doesn't tell you anything. But it has, if you go away and have a look on in the documentation, if you look around the place, you'll find Erlang OTP kind of go like, I don't want to even say it, but I will, Ruby and Rails, so, you can't really use Erlang without using OTP. Well, if you are, you're kind of doing it wrong. OTP is a set of ideas, it's a set of modules and standards for building distributed programming systems. And essentially, this little diagram is one key aspect of it. That you have these little components of execution. This is like the unit of program that you need to think about. You start something, you have to initialize it. Spawn means it comes from somewhere else, and then you sit on a loop responding, and that's essentially the pattern that is at the core of this thing, Cloud Haskell. That's what the guys borrowed from Erlang and from the OTP library. So what is it? It's it's a system for it's a set of libraries for supporting building distributed programming. And when I saw it, I started my project using Async. And then I saw it sitting there, and it was fairly new. This was a few years ago, and I thought I really want to use that. And I looked around and discovered that almost nobody was using it. So, which was a little concerning. But I persevered. The crucial feature for me, I had the choice. I could have switched to Erlang and used their OTP libraries. But these guys promised that actually I didn't need to do that. I could just stay in Haskell. I like Haskell. I can just carry on using Haskell and get all the coolness of OTP and Erlang style programming. So that promise is actually pretty great. But crucially for me is that it builds on all of the other Haskell libraries. So we use a lot of other Haskell libraries that are really powerful and useful, and tooling and everything else. So I wanted to stay in that Haskell ecosystem, and Cloud Haskell allows you to do that. I'll just talk through a couple of the kind of key ingredients. I guess there's this there's this TCP-based networking layer. So there's a library there called Network Transport-TCP. So Network Transport is a package library that provides the interface for setting up the transport, the information, the communication transport layer, and TCP is the canonical implementation of that over TCP. Actually, there's a bunch of other ones there. You can use other protocols for communicating, including shared memories and blah, 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 lots of things, but TCP is what everybody uses. It's the most useful thing. And then there's this distributed process package, which has the process abstraction, and that's the kind of the core piece of the whole thing. It has built into it support for serializing data and closures, and that closures thing is kind of cool. It allows you to serialize function calls and send them over the wire and have them execute in some other machine. We haven't actually used that a hell of a lot, but it's there. And finally, there's this whole monitoring infrastructure, which is a core part of the TCP system that's about standing up, running a process and then saying, oh, just keep an eye on that for me. If it falls over or disappears for some reason, do something, respond, bring up another one, whatever. Erlang's attitude is that you write things to just crash and burn. Anytime something goes wrong, you just throw it away and start again. And I started with that idea in mind, but actually I've found that I haven't needed to worry about it, because actually the type checker in Haskell has meant that my code doesn't crash and burn, pretty much. And that's really great. So I've only used that a little bit. So this is just a little bit. I'm going to run through a few of these code slides because we're at a coding conference, so you have to do this a little bit. I have done this in the past, and I didn't load this into GHCI, and so this time I loaded everything into GHCI. It all works. It all type checks. So, so if you find an error, then I'll be very surprised. So this is how you kind of you step into the world of Cloud Haskell. You have to give it some TCP type information, ports and hosts and so on, and then you try and create a transport layer, and of course that can fail, usually because somebody else has already got your port, and then you can stand up a node, and finally you run your process in the node, and that application, line 17, 18, that's where most of your actual writing is. All that other stuff is sort of essential boilerplate. You might have, in the real world, you'd probably have some options there, and you might have some modes and blah, 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 database connections, etc. But that's essentially the boilerplate for that. And in here, we're talking about local nodes and processes, and those are the two of the core abstractions. A node is essentially a dot in your graph of your infrastructure, and a process sits inside that. So the nodes have a reference number. There's a namespace, kind of a DNS thing. Well, it's sitting on top of DNS, so you've got your host name and your port, and then which node on that port. You can have multiple nodes, and that's and then the process is actually a monad that sits around that and allows you to run code that communicates with all of the other nodes and processes running in your infrastructure. So once you've stepped into the world, then suddenly you've got everything available to you. So I'm going to just talk about this bit of code here. Essentially wraps up that Erlang style concept. We've got I haven't got the spawn's somewhere else, of course. Then we're initiating here. The register line there essentially says to the whole Cloud Haskell, the whole network of your system, this is who I am. This is, if you want to find me, here I am, and allows other processes in other places to find this particular process. And then it sits on a loop with that expect call, and expect will just block until it's getting something, and then this case statement, this is very idiomatic Haskell. The great thing is that it will, when the message comes in, it'll try and match it to this type, and then do something useful. In this case, it just grabs some state out of an STM var and chucks it back at the caller. There's one slight problem here. There's this thing, pair get state, is coming over the wire. That's the message that came from somewhere else. And it's got this thing inside it called pair. If you look at the type signature at the top, you've got a tvar state. So state and pair get state are symbols that I've not defined in this code. And if you tried to load this, it would immediately complain about that. And yeah.
Clarify, is pair get state something you've written, or is it Cloud Haskell?
No, it's something I've written. Yeah. So yeah, in my original slides, I actually had all of the functions that we were pulling out of the libraries there. Sorry,
But message is your custom type.
That's right. Yeah, exactly. Yeah. So message and so expect is core. Get self ID is core. Register is called forever. Send, chan, read, these are, but all the others are mine. So I've just talked about that. This little bit of code allows, this is me defining these data types, and this is where, for me, Haskell really starts to win big time, because I can load these language pragmas and tell it to generically derive all my binary instances, for example. And so I don't have to write any binary instances at all. It just automatically figures all that shit out in a useful way. And in this case, the pair get state is actually sending back a send port. A send port is one of two ends of a channel which is typed, strongly typed, and so your whole program has to make sense, if you like. It has to be consistent across all of the different processes. So these are the binary instances that are essentially serializing, deserializing across the wire, and using generic. So there's type channels. I just mentioned that. Sorry. So, one thing that's really useful for me is this software transactional memory. So Erlang has some support for distributed databases and so on, and you can use some of them, but STM is so awesome that Cloud Haskell really just leans on that quite a lot, and it's very recommended. These are the guys who are involved. This is not my last slide, by the way, so that's, I just wanted to thank all these guys, and in particular Edsco. Edsco gave me about 3 hours one evening with my code sitting in front of him. We talked through it. That was really awesome. He helped me understand the architecture of it. I think that Duncan and Edsco wouldn't be too offended if I said that the documentation around this is a little ropey in places. It's not the clearest, but you can grab them on IRC. You can ask them questions. So that's pretty great. So how did we use this? So that guy had this problem years ago of trying to de-escalate the Cold War. Half of you guys can't remember that shit, right? Because that was ages ago. When I was a kid, that was terrifying. You were going to die any moment in a ball of fire. I'm not a huge fan of this guy, but this problem was hard, and the way he solved it was by essentially setting up a whole lot of agreements and then verifying them. And what's been happening in science is kind of the same. So for a while, people would be happy with saying, expert scientist says blah, 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 and you believe them because they're a scientist and they've got a PhD, and you don't. Now it's not enough. Now people want to be able to actually check what you've done. They want to be able to verify everything, and that's been driving this kind of reproducible research concept very strongly, and we have been embracing that at Dragonfly. We do environmental and ecological research mostly, not only, but other things as well. And that involves running lots and lots of code, lots of modeling code, lots of machine learning code, and when you throw that into the community, people say, "Oh yeah, that looks good, but how do I know it's true?" So we have to make sure everything is reproducible all the time, and the only way to do that really effectively is by continuously integrating it. So people, you guys are all very familiar with continuous integration. The science community is not. When you say continuous integration to a scientist, they go, "What?" That's the other one, yeah. Version control, continuous integration are incredibly powerful tools that are so much more useful than software engineering, in my opinion. And we are certainly using them. And as you do, and this is a kind of a joke, we called it Gorbachev. So this is our, we're up to our third continuous integration platform. I suppose it's like some people have weaknesses for writing parsers and templating libraries. I like integration systems. So this is our system. It's actually now deployed across 2 different organizations, and it's used, a lot by a lot of our team and others. Some of our clients are using it, so it's starting to get busy, essentially. And the Cloud Haskell version of it, we started off with Python version of it, and this latest iteration is actually a lot better. It allows us to scale in a way that we didn't used to be able to do. We ran late last year, I think, we ran a project which involved about 3.5 years of compute time on the Amazon cloud. We actually ran it in about 2 months, and it involved spinning up thousands of instances on hundreds of EC2 nodes. And I knew we were doing something cool when Amazon gave me a call. It's like, what are you doing? So that was cool. Conclusions, Haskell ecosystem has a lot of really great advantages, which we all know about. These are the ones that really stand out for me. It's outrageously stable. Erlang said it's got all of this infrastructure about dealing with faults. I just don't have those problems. It just doesn't happen hardly ever. Performance is really great, and the easy refactoring is also awesome. And this last one is probably goes back to that talk from Alistair. I think this is really crucial. I would kill myself if I had to write all my days in C#. That would just be a slow death. And the other people like you guys who are really who find this stuff exciting tend to be really smart and engaged and interesting. So that's me.
See if these microphones still work. Lee, you want to? Oh, do we have questions? We have questions. Do we have time for questions?
Yeah, one.
We have time for one question. Yeah. Yes.
Okay.
Yes. Let's. Yeah. You can have this one.
I'm told by people that like Erlang that the process monitor is one of the most important parts of the system.
Yeah.
And you may say, Riley, yeah, okay, but I would like to know something more about the Haskell monitoring tools.
Yeah,
when
so
they are needed.
yeah, so I mean, I guess I can. I skipped over them in this slide, and I haven't. This is so the tools essentially allow you to set up monitors in the Erlang model, which says you have another process whose only job is to accept exceptions that occur over on some other. And those exceptions can occur for multiple reasons, but in particular around network faults. So you can then act on that and make a choice on what you want to do. The network fault tolerance, I think, is the crucial one. And of course, that's not solved by Haskell, right? So, you know, I was a little flippant about that. So, yeah. I can, if you're interested, I can show you around the documentation how to find out more about it. Yeah.
Thank you.